This is the fourth section of the chi-squared test chapter, and here we're going to be looking at doing chi-squared tests with discrete distributions. So these could be either discrete uniform distributions, discrete uniform. So we're talking about things when you've got like these tables and things like the outcome of dice, things like that. It could be a binomial distribution. So remember, we have our parameters n and p. So we're looking to see, we've got a set of numbers, could they fit a binomial distribution? And then the other one is a Poisson distribution. So this is where we just have our one parameter, the mean, and again looking at some observations and seeing if they could be modelled by a Poisson distribution. And remember, with a goodness of fit test, basically all we're doing is we are calculating the spread or the variance, I'll put that in quotes, the variance of our observed data, compared to our expected data. Yeah, and you'll remember that we can use this simplified formula of the sum of the observed squared over the expected minus the observations. Now we're going to be doing some examples of all the different types of distributions, and you'll see that there are some slight differences depending on the distribution. Right, so you've got 100 digits between 0 and 9 are selected from a table with frequencies as shown. Could the digits be from a random number table? Test at 5% significance level. Right, so the first thing is, if the digits were from a random number table, we would expect each value or each digit to come up around 10 times. Yeah, if they were truly random, every digit will have an equal chance of being picked. So what we're going to do is we are going to work out the variance of these numbers, again in quotes, this word variance, of the digits we have here and their frequency compared to what we would expect them to be. So since we're doing a hypothesis test, the first thing we need to do is to say what H0 and H1 are. Now H0 is going to be that, well, if they're all expected the same number of times, it's a discrete uniform distribution. Okay, so H0, the digits could be from a random number table. In other words, the data fits a discrete uniform distribution. Okay, and H1 would be the digits are not from a random number table. So that's step one. Next step is to write down what the expected, and I'll have to put it here, what the expected frequencies are, and they're all going to be 10. Down here, my frequencies above is what has been observed. Now, since none of the expected frequencies are less than 5, I don't need to combine any cells, so just put that over here as a note. No combining of cells since no expected frequency is less than 5. We do need to say what the degrees of freedom are, so that's just going to be the number of cells minus 1. Okay, so 9 degrees of freedom. We'll use that when we look up the critical value in a moment, but now we're going to work out our value for x squared. So x squared is the sum of the observed over the expected minus n, the number of observations. So that will be the sum of, and actually won't write sum of because we'll actually write the calculation out. So we're going to have, start with the first column, so 11 squared over 10 plus 8 squared over 10, there's going to be a few of these, isn't it? 8 squared over 10, already I'm messing up the brackets. Tell you what, let me pause it and then write the rest down. Okay, so here you can see the full calculation written out. So here we have our observed squared over the expected for each digit. Then we find the sum of those, and divide by 100. Now when we work that out, the bit in the brackets will be 1062 over 10 minus 100, and when we work that out we'll get a value of x squared as 6.2. So now we will use the tables and look up chi-squared for, what did we say, 9 degrees of freedom, and we're going to find the critical value, and this is going to be for 5 degrees significance level, so at 5% significance level. Right, so on page 192, so just put a reminder there, this is page 192 in the book where you will find the tables, and it's also in the formula book as well, so you don't need to memorize all the values, which is useful. And we get a critical value, or value of x squared, of 16.919. Now what does that tell us? Well, the variance, and I use this word variance loosely, our variance that we worked out, the spread was 6.2, and the table says you can go up to a spread of 16.919 and it will fit the distribution. The lower the spread, the better it fits the distribution. So in this case, our calculated value of x squared was less than our critical value. Okay, less is better. Less means a better fit, less spread from H0, which means that we accept H0, and then we just write our conclusion that the digits could be from a random number table. So you just copy out what you wrote for H0, could be from a random number table. Right, the data in a table are thought to be modelled by a binomial distribution with n equal to 10 and p equal to 0.2. Use the table for the cumulative distribution function. We're not going to use a table, we're going to use a calculator, and I'll show you how to do that in a moment, to find expected values and conduct a test to see if this is a good model. Use 5% significance level. So since it's a hypothesis test, H0 will be that the binomial distribution is a good model. Distribution is a good model. H1, the binomial distribution is not a good model. Is not a good model. Right, so expected frequencies, calculating expected frequencies. Now we're not going to use the tables, we're going to use our calculator. So the first thing we're going to do is to press menu and 7 to take us to the distribution menu. When we've done menu and 7, after that we do number 4, which will take us to binomial PD. Now when we've pressed 4, we're now going to press number 1, because we're going to be using the list function to get a list of all of the expected frequencies. So when I press that, I'm going to type in the values of x, so 0.1, 0 and then 1 and then 2 and 3 all the way up to 8 in that column, press equals, type n as 10, p as 0.2, and then in a couple of seconds I get the table. Okay, so what I'm going to do now is I'm going to pause this in a moment, and I'm going to put in what those probabilities are here, because it's going to take a little while just to copy them down. Okay, so 0, 1, 2, 4, 5, 6, 7, 8. Okay, so now I've calculated the expected probabilities. I think I put expected frequencies there, I haven't quite done that yet. The expected probabilities is what I've calculated. I'm now going to calculate the expected frequency here, expected frequency, and the way I'm going to do that is that we need to take each expected probability, which is this, and we times it by n, which is the total number of observations, and I'm going to get that by adding together all of the frequencies. That will give me the total number of observations. So it's going to be 12 plus 28 plus 28 plus 17 plus 7 plus 4 plus 2 plus 2 plus 0, and we get 100. That's handy. Okay, so each probability times by n 100 to now get the expected frequencies. So we'll do those now. So 10.73, 26.84, 30.19, 20.13, and then 8.8, 2.64, 0.55, 0.078, and then 0.0073. So these are my expected frequencies. Now we need to look to see whether I need to combine any cells. So do I have any cells where the expected frequency is less than 5? Yes. These ones down here. Now if I combine those, I don't get a value bigger than 5. So all of these here need to be combined with the 4. yeah, because just combining 5 to 8 doesn't give me an expected frequency greater than 5. So now my table's going to look like this, with x at the top, and I'm going to have 0, 1, 2, 3. Now basically anything 4 or more, so greater than or equal to 4, is going to get combined in that cell. So at the bottom here I'm going to have my expected frequencies, so 10.73, 26.84, 30.19, 20.13, and then I now combine 8.8 with 2.64, 0.55, 0.078 and 0.0073. So that will give me 12.0753. So now I'm going to calculate x squared, which is going to be the 10 point, so this is my observed squared, or the sum of my observed squared over my expected. Oh, so it's the other way up, isn't it? My observed was 12, so observed squared 12 over my expected 10.73 plus next observed squared was 28 over my expected. Then my next observed squared, that was 28 over my expected. Then the next observed squared, so the 3 observed 17, so 17 squared over my expected. Now for the last set of values, I need to combine all of these because I combined those cells, didn't I? Yeah, so my observed squared isn't going to be 7, it's going to be 7 plus 4 plus 2 plus 2, which is 15. So my observed is going to be 15 because I've combined the cells over the expected. Okay, and then we'll work that out, and then we'll subtract the number of observations, which was 100. So let's work that out and see what we get for x squared. So that gives me 1.589. There's a 0 after that. Now from the table, and I've got a little bit of space up here, let's look up chi-squared, and it's going to be 4 degrees of freedom, since we can see here that I have 5 cells after combining. So 5 minus 1 is 4. So that's going to be our value for the degrees of freedom. So we can use that now to look up the critical value. And this is at a 5% significance level. So at 5%, and I can see it's 9.488. 9.488. Now, how does the spread of our data compare to our chi-squared value? Well, it's less than it, isn't it? Yeah, so 1.589 is less than that, a lower spread, which means that we can accept H0, and then say the binomial distribution is a good model in this particular case. Or we could say something like, there is evidence to suggest that the binomial distribution is a good model. Okay, the study of a number of girls in families with 5 children done on 100 such families are summarised in the table below. It is suggested that distribution may be modelled by a binomial distribution with p equals 0.5. Give reasons why this might be so. Well, when can we use a binomial distribution? When there's a fixed number of trials, and that is they're looking at the number of girls in families with 5 children, so n equals 5 in this case. So we've got a fixed sample size. There is also probability of success or failure, failure. In other words, it's either a girl or it's not a girl. And these trials should be independent. Yeah, so going to a family of 5 and finding out whether they've got boys or girls should be independent of going to a different family with a family of 5. So fixed sample size 5, probability of success or failure or independent. So that's 3 good reasons why this could be modelled with a binomial distribution. So part B, test at the 5% significance level whether or not a binomial distribution is a good model. So let's start with H0 and H1. The binomial distribution, and you can state what that is in the question. I suppose we should do, because it doesn't say the binomial distribution with n equal to 5, because that's our sample size, is a good model. H1, basically exactly the same thing, but with the word not there instead, is not a good model. Let's write it all out. So now we're going to use our calculator to work out the expected frequencies, expected probabilities. So I'm going to have x here, 0, 1, 2, 3, 4, 5, and then once I've got the expected probabilities, I will use that to work out what the expected frequencies are. So this column is going to be what the expected probabilities are, so I can put those in because I've got that on the calculator. So 0.0, so remember, go into the menu 741, so you've got the list, you type in the values of x, and then you can just get your probabilities all listed. So, and then these two are the same. Now because p is 0.5, I'm expecting this to be symmetrical. I should get the values at the same values at the other end. Yeah, 1562, and then the last one's the same as the first one, 0.0312. So now I'm going to work out my expected frequencies, and I do that by taking my expected probability and timesing it by the number of observations, and it's 100, it says up here, so that's the number of observations, because 100 different families. So I take my expected frequencies, times them by 100, they're going to go in the last column. So I will get 3.12, 15.62, 31.25, 31.25, then the same at the bottom, 15.62, and then 3.12. Now you can see I've got expected frequencies here less than 5. Okay, so they need to be combined with a cell there. So those are going to be combined, and then I can use that to help me work out what x squared is. So if I do the table this way, so my values of x, now I'm combining 0 and 1, so I could say less than or equal to 1 child. It's going to go there. Then I'm going to have 2, 3, and then 4 or more. Basically it's 4 or 5. Because it's not going to be any more than 5. So I'll put my expected frequency here in the bottom row, and I'll be ready to work out x squared. So I'm going to have the 3.12 plus 15.62, so that's going to be 18.74. So I'll have 18.74 here and at the end, and then I'll have 31.25 for these two. Now because I've combined those, it also means that these need combining and these need combining as well when I work out x squared. So I'll have 31 at that end and 11 at that end. So now I'm ready to work out x squared. So I think I probably need, I don't know why I made these lines so long. Let's make that table a little bit smaller, like this, because I'm always running out of space for working. There we go, like that. So x squared is going to be the sum of all my observed squared over my expected. So 13 squared over 18.74. Oh, sorry, not 13, 31 squared. Because I'm combining them, aren't I? 31 squared over 18.74 plus 38 squared over 31.25 plus 20 squared over 31.25 again plus 11 squared, that's the last two combined, over 18.74 squared, also over 18.74, don't square it, minus the number of observations, which was 100. So let's work that out. So I get 18.354. Okay, now the number of cells after combining was 4, so the number of degrees of freedom is going to be 4 minus 1, which is 3. So we're going to use our tables, 3 degrees of freedom and 5% significance level to find the critical value, and that gives us 7.815. Now on this question, this time we have our observed value, our x squared, is greater than what we found in the tables. Okay, so it's greater than that observed value, so in which case we would reject H0 and we would say something like, there's evidence to suggest that the binomial is not a good model, so binomial with those values that we've suggested, where we have 5 and 0.5, is not a good model. Okay, so in this example we've been asked to actually estimate P, and if you have a question where you're seeing whether a binomial distribution is a suitable model for the data. If we want to estimate P, the probability, the way that we do that, it's the total number of successes, divided by the number of trials times by the number of observations. Now, if we were to actually write that down as a formula, so it's the sum of basically our data times by the frequency of that piece of data divided by n, which is the number of trials. That just comes from the n part of the binomial distribution, times by n, which is the total number of observations. Okay, so we're just putting letters in here. Now when you estimate P, what happens is that you now have one less degree of freedom. Okay, so this means we have one less degree of freedom. Okay, so that means that when we estimate the number of degrees of freedom, it's going to be the number of cells minus 2. Number of cells minus 2. So that's important because normally we've just been taking one away, and that's after combining again. So the first thing we're going to do is we're going to estimate the probability, and that way then we can set up H0 and H1. Using a formula, we're going to have 0 times 13, so we're going to have the sum of these, plus 1 times 18, plus 2 times 38, plus 3 times 20, plus 4 times 10, plus 5 times 1, so that's R times the frequency of R, so that's the total number of successes, over N, which is the number of trials. Remember, it was 5, and the number of observations was 100, wasn't it? So let's work this out, and we'll get 0.398. So this is our estimate for P. So now this question is about seeing whether this data fits this model. Now with this probability rather than 0.5, so H0, now we can do the binomial distribution with this 0.398 is a good model, and then H1 would be that the binomial, I'm not going to write it all out again, binomial with this n equals 5, P equals 0.398 is not a good model. Right, now we use our calculators to work out the expected probability, and from that work out the expected frequency. So I'll pause this and complete the table. So those are my expected probabilities. Now I know that I need to multiply that by the number of observations, so I'm going to be timesing those by n to get the expected frequencies. Again, I will pause that and put the answers in. So here's my expected frequencies. I can see that this needs to get combined with that, so that will give me this last row of the table will be 4 or 5 now once I combine, and then if I do 7.55 plus 0.99 I get 8.54, so this will become 8.54 after combining. So now I'm ready to work out x squared. So that's going to be all of my observed squared over my expected. So I need to remember that I have combined these two, so that will give me unobserved of 11 because I've combined it from my expected frequency table. So that will give me observed 13 from the first one, 0, 13 squared over 7.9 plus 18 squared over 26.13 plus 38 squared over 34.55 plus 20 squared over 22.84, and then the combined one 11 squared over 8.54, and then I need to take away the number of observations. Well, that's 100. So let's work this out and see what we get. So this time I get 7.268. It carries on, there's a 1 after that. So this time when we look up chi-squared, so the number of degrees of freedom this time, the number of cells after combining was 1, 2, 3, 4, 5. But now I need to take 2 away from that because I did this estimation of P. So this is going to be 3. So that was because we had 5 cells after combining, and we take away 2 because of that estimation of P. So I'll look that up to find a critical value. Oh, and this is at 5%. Keep forgetting to put that in. 5%. So let's see what we get. Turn to the back of the book or the formula book if you've got it. 3 degrees of freedom, 5%, and I can see 7.815 as my critical value. 7.815. Now let's have a look. My value of x squared is less than the critical value with 3 degrees of freedom. Right, what does that mean? That means that we accept H0 because that spread is small enough. And now with the estimation, it is a good model. So the binomial with n equals 5, p equals, what did we estimate p as it? 0.398 is a good model. So the number of telephone calls arriving at an exchange in 6-minute periods were recorded over a period of 8 hours with the following results. Can those results be modelled by a Poisson distribution? Test at the 5% significance level. Now in this question we are not given lambda, we're not given the average rate at which calls occur, so we're going to have to estimate lambda. Now the way that we estimate lambda is it's pretty similar to the one that we do for binomial. So the sum of the value of r times its probability divided by this time n, because there is no n for the number of trials, so that will estimate probability. And just like before, if we're estimating lambda, okay, so if we estimate lambda, we lose a degree of freedom. So the number of degrees of freedom is going to be the number of cells after combining minus 2, just like before. So the first thing we need to do is to set up the hypothesis test. But before we do that, what we will do is we are going to calculate lambda, or estimate lambda. Right, so this will be 0 times by 8 plus 1 times by 19, 2 times 26, 3 times 13, 4 times 7, 5 times 5, 6 times 1, 7 times 1, and then 8 times 0. I'll leave that out, I'll actually write it here, plus 8 times 0. Now we need to divide that by the number of observations. Now let's think about it. There were observations every 6 minutes, so that means that there were 10 observations in an hour, 10 obs in an hour. Okay, which means that there must have been 80 observations in 8 hours. So total number of observations is 80. So my estimate for lambda is 11 over 5, which is 2.2. So now I can say that my H0 is going to be that this problem 2.2 is a good model, and a Poisson model with 2.2 for H1 is not a good model. So now we're ready to work out our expected probabilities, and from that we can work out our expected frequencies. So just like before, menu 7, but now because we're doing a binomial, we're going to scroll down and go to Poisson CD, list like before, and put in the values of x, so that's 0 to 8, press equals, type in 2.2, let the calculator do its stuff, and we'll have a table of values. So I will put those here. Okay, so again I will pause so that you can see the expected probabilities there. Okay, so this is now the table of the expected probabilities. I can now work out the expected frequency, and I'm going to times each one of these by 80. Okay, so here you can see our expected frequencies. So I can see that these expected frequencies fall below 5, so they're going to need combining. So we can combine those to create a value greater than 5. So if we combine these here, then we actually get an expected frequency of 5.744, which means that I can combining basically 5 or more here, 5 or more, and if I'm combining those, it means that when I do my calculation, I need to combine these to give me a frequency of 7. Okay, so when we do the calculation to work out x squared now, so we're going to do 8 squared over 8.864 plus 19 squared over 19.496 plus 26 squared over this plus 13 squared over this plus 7 squared over this. Okay, when we find the sum of those, what we get is 82.196. Okay, then I need to take away n, the number of observations 80, so I'll get a value of x squared of 2.196.8, if that's to 4 dp. Now I need to look up my critical value. Let's do this over the other side. Now how many degrees of freedom we got? So we had 1, 2, 3, 4, 5 cells after combining, because we had to estimate lambda. Actually no, not 5 cells, 6 cells after combining. So I'll just write that down. 6 cells after combining, and since we've had to estimate lambda, the number of degrees of freedom is going to be 6 minus 2, so we have 4 degrees of freedom. So now I'm going to look at chi-squared for 4 degrees of freedom and 5% significance level, and let's see what critical value we get in the table. Just finding it here. Here we go. 4 degrees of freedom, 5%, and we get a critical value of 9.488. Okay, I need a bit of space somewhere to write a conclusion, so let's take this out. So my value, my x squared, was less than the critical value. Okay, so that means except H0, except H0. And then we can say that this Poisson with a rate of 2.2, okay, is a good model, or there's evidence to suggest that that is a good model. Okay, you should now be able to do exercise 60 on pages 110 to 113. So don't forget, we want to use the quick way to work out x squared, which is going to be the sum of the observed squared over the expected minus n. There may be times where we need to estimate p, or we may need to estimate lambda. So just to recap on how we do either of those. So if I want to estimate p, that's going to be the sum of r times its frequency, so the outcome times its frequency, divided by number of trials times by n. If we need to estimate lambda, then it's very similar, but here we just divide by n, which is the number of observations. And when we estimate this, we lose a degree of freedom. So lose a degree of freedom. So that means that to calculate this, it's the number of cells after combining, but we take away 2, and that's going to happen when you need to estimate that. And remember, use the list function on your calculator, to get a list of all of the probabilities. So once you've done the list function, that will help you calculate the expected probability for each outcome. And then once you've got the expected probability, you're going to use that to work out the expected frequency. And the way that you work out the expected frequency is you take the expected probability and you times it by n, the number of observations.